Okay, so we're going to take a look at number 18 here. And in number 18, we are told that a proton of mass p, a deuteron of mass 2 mp, and a charge equals e, and an alpha particle, m equals 4 mp and q equals 2e, are accelerated by the same potential difference, and then enter a magnetic field B, where they move in circular paths perpendicular to B. Now, in the previous class, I solved this problem assuming they have the same velocity, because I didn't catch the fact that they are accelerated by different potential differences. So let's actually do this problem correctly.
You got the right answer.
Well, no, actually we didn't, but nobody noticed, which is poor. All right.
Teacher doesn't the right answer.
Right. Well, no, it does happen, and it happens mainly by not noticing little details, right? And so the question then is, find the radius of the circle for each one of these. Now, previously we talked about a charged particle going through a magnetic field, and when that charged particle goes through the magnetic field, what shape does its path take? Circle. And why is that?
Because it's going to push always one way.
It's getting pushed not always one way, but always something. Always how is it being pushed? Left. To its path. Yeah, that's right. It's being pushed perpendicularly to its path. And so as a result, it moves in a circle. Now, we can say more. Because since the force is equal to QVB, sine of 90 degrees, which is invisible, and that is also equal to mv squared over r. If I now cancel a factor of b here and solve for r, I get mv over qb. Please don't try to memorize this as a separate equation. It's easy enough to derive. Force equals force. Solve for the radius. But now what we notice is that the velocity is a factor here, and the velocity will not necessarily be the same for these particles. In fact, the velocity is not going to be the same for these particles. And the reason for that is simple. The particles have different masses, and they have different charges being accelerated by the same voltage. So our first order of business is to find the velocity in terms of the voltage. So they give us a label for the voltage.
V?
Potential difference, capital V. Yep. So let's work this out for the proton. For the proton, the amount of energy that it's going to receive is going to be E times its potential difference V. And that is also equal to its kinetic energy as it goes into this circle. Please notice that the little v on the right-hand side is different from the potential difference, capital V, on the left-hand side.
Science or mechanics.
Yeah. And so the speed that I get is root 2ev over mv. What changes if we now talk about the deuteron? Let's give the deuteron its proper symbol. A deuteron is a hydrogen atom that has a neutron in the nucleus, as well as a proton. And because of that, it actually is, well, it's significantly different from the hydrogen atoms. It's twice as heavy, right? And because of that, if you have water molecules that have had their hydrogen replaced with deuterium, those water molecules are going to be about 10% heavier than normal water. And so it's called heavy water. And it was used heavily for the uranium enrichment process because heavy water can moderate neutrons coming out of uranium. So it was used as a neutron capture method during World War II and surrounding that. Graphite was a whole lot better. So graphite quickly superseded heavy water for that purpose. And in fact, the Germans made a significant strategic error. Werner Heisenberg had calculated wrongly that graphite would not work to moderate neutrons. And he would not let anybody check his calculations. And as a result, the Germans used heavy water, which is a lot harder to work with because it's liquid. And as a result, they lost the race to the atomic bomb and they lost the war.
Wow. 6 points.
So there you go. Well, back to our story here. What changes now if I plug in values for the deuteron? What doubles? Don't say it. The mass doubles. All right. So that means that I'm going to replace. What about the charge? The charge is the same. And so what I get is that this, that the factors of 2 cancel each other. Now, how does this compare to that right there? If this is the velocity of the proton, then you can see that the velocity, or the speed, I should say, of the deuteron is going to be different by what factor? Root 2, specifically 1 over root 2. The speed of the deuteron is going to be 1 over 2, root 2, times the speed of the proton. Everybody on board with that? Now, how about the alpha particle?
Wouldn't that just mean it would be twice as much?
Wait, what?
If you don't you have to because we don't. I mean, in math, you don't let the radical 2
Sure I did. I love the radical 2.
on the bottom.
Oh, good little radical 2.
This terms are big. You don't want radicals in your basement.
He is.
Oh, so that's an older school rule.
Just
And where it comes from is this. Suppose I have to calculate by hand, but I don't have a calculator. 1 divided by root 2 is 1 divided by 1.41428 something. I don't want to do that. But root 2 over 2 is 1.41428 divided by 2, which is 0.707. You can do it in your head. So this kind of... You can't do 1414 divided by 2?
Oh, yeah.
Oh. My turn to laugh at you. All right.
But the way you said that, it was just so... Yeah, you guys...
So back in the day, it was sort of decreed that when you had radical expressions like this, you would rationalize them so that you would end up with radicals in the numerator divided by whole numbers in the denominator. With the advent of calculators, it doesn't matter much anymore. So there you go. All right, now for the alpha particle. The alpha particle, which sometimes carries the symbol alpha, but usually carries the symbol helium-2+, because it is just a helium nucleus with 2 protons and 2 neutrons and a charge of 2+, because it has no electrons.
what did you say that was called?
Alpha. So
Wait,
if you
how would
hear
you
about
know
alpha
this?
radiation, that's what that is. Beta radiation is just electrons that are being emitted by nuclei as they split apart. And gamma rays are high energy photons that are being emitted as the nucleus shifts to a lower energy state within itself. Okay?
So how would we know that it would be that?
Because I'm telling you. I'm giving you, I'm letting you know about culturally important things.
So you can identify types of radiation.
That's right. And so if we now calculate the velocity of or the speed of the alpha particle, then we're going to do the same thing, but what changes now?
That's supposed to be a V.
Yes?
Like
Getting
the
picky,
potential?
aren't
I didn't know if you were talking about potential. I don't know.
Okay, so what changes now?
Like pass triples once again, so quadruples from the beginning.
Four and P's.
Charge doubles.
Yes. What do you notice? These guys cancel, leave me with a factor of 2. So how does that relate to the other speeds that I have?
And it's just another, it's one of the two, so it's just a half.
1 over, okay, you're going too fast. Give me some nouns. What's 1 over root 2 of what?
It's, you have, it's the same as,
Stop it with the it. Nouns.
yeah,
The velocity for the
because
zero.
you have to multiply by,
That's not even a complicated explanation, I just need nouns.
you have, it's just another factor of 1 over,
Stop using the
multiply by
word
1 over
use
root 2.
English.
Multiply what by 1 over
The
root 2?
VP, and that's the same as the,
Okay, let's try that. If I take and multiply this by 1 over root 2, no, I get that, which is v deuteron. Ah, if I multiply v deuteron by 1 over root 2. See, you weren't as clear as you thought you were.
like, I knew what I was doing right
No, no, no. You weren't as clear as you thought you were. You thought you knew what you were doing. Well, what you needed to do to carry it home is to use nouns and then check. And once you checked, you saw the mistake and you could fix it.
So, how do one
Now,
get?
what is V alpha in terms of V proton then?
One over radical 2.
Vd is 1 over root 2 Vp. V alpha is 1 over root 2 Vd. So V alpha is what in terms of Vp?
1 over 2, 1 over root 2 VP.
That doesn't seem right. Because if that were the case, then Vd and Vp
Well,
would be the same.
isn't it, oh wait, no, it's
2 times
1,
over root
yeah, and then you like,
2.
just plug it in.
Okay, well do it. Tell me. You don't need a calculator.
1 divided by root 2 times 1 divided by root 2 VP.
And what is root 2 times root 2?
2.
Yes.
So how do you get root 2 in the beginning from the,
It's square root.
Here. Is that what you're saying?
yeah, I mean, they cross out.
I understand that. What we're doing is we're comparing this one to this one. And what we notice is, let's do it like this. Suppose I pull the root 2 out of here.
Okay.
And you can see that this is equal to Vd. So that Vp is equal to root 2 times Vd. And now if you just divide, you've got it.
This doesn't explain how you get the root 2 on the bottom of,
Yes, it does. Pull the root 2 out of here.
okay.
This is Vd.
Yes, but,
Root 2 Vd equals Vp.
okay.
It does explain.
I got it.
Okay, this was the hard work, and this was the stuff we didn't do in that other class, so we're special. That's okay, I'll put this video up for everybody to see. Okay, so our results so far are these. V alpha is the same as 1 over root 2 Vd, is the same as 1/2 of Vp. Now what we want to do is to go through and compute the radii, and we've already done the hard part. We've already computed
The velocity.
that radius all the way back up to here is equal to mv over qb. And now let's go through and do that for the proton, for the deuteron. I'll give them the correct symbols. Proton is just the bare naked hydrogen atom. Deuteron is twice that. And the alpha particle is the helium nucleus. And so we're ready to compute the radius of the proton. All right, here we go. What's the mass of my proton?
That's a
You must
1.6
use the
times
label
10
that's
to the
given.
negative 19.
Use the label that's given. What's the
That's
label that's given in the
mass.
problem?
That would be charge.
MD. And we're going to use the VP that we've had before. What are we going to use for the charge?
1.6 times 10 to the negative 19.
What label are we going to use for the charge? Right. I don't want to clutter it up with numbers too much, all right? All right. Now, how about the deuteron? What changes?
Mass doubles.
Mass doubles. How about the speed? Yeah. How about the charge? Yeah. And now we've got some factors here. What's 2 divided by root 2? 2 divided by root 2. Root 2. That should not be a hard question. How does that compare to the RP that we have here? It's multiplied by root 2. Or better, since we're on an anti-pronoun kick, it is RP times root 2. And finally, for the alpha particle, what changes here in our expression? 4 in P's. And, yep, 2 EV. So what's 4 times a half divided by 2? 1. And how does this compare to the radius of the proton? The same. Here you go. Now this is a complicated example of a comparison problem. And the reason I say it's complicated is that we had 2 different things that we were comparing. One thing that we were comparing was the speeds accelerating through a constant potential difference. And the second thing that we were comparing was the radius for these different speeds. Okay? But the method was basically the same in both cases. I plugged in 2 times the value or 4 times the value or whatever it was, and I related it to the original simply by substituting. Now that we're done with the comparison problem, let's come back and understand why it worked out the way it did. First of all, it's pretty easy to see why the speeds worked out the way they did in this equation right here. Because every time I double the mass, I get a factor of 1 over root 2 times the speed. And the reason for that is very simple. Because kinetic energy is equal to 1/2 mv squared, if I double the mass, take the square root, my speed is going to be root 1 over root 2 times the original. It takes more energy to accelerate a longer mass. Then the second thing that's even more interesting is how the factors worked out here. Because we had 3 different changing factors. The only thing that remained constant in our problem was the V. And in the first computation with the deuterium, I guess the second computation with the deuterium, we had twice as much mass, and our speed was 1 over root 2. Charge was exactly the same. And so the additional mass caused the radius to sweep out further because the magnetic field was not able to exert enough force to pull it around in the same distance. See what I'm saying? It's the difference between driving a U-Haul and driving a sports car. the U-Haul has a wider turn radius.
But it ended up being the
I
same.
hated drinking my dad's truck. I used to have a big ass trucks are so much fun. It sucked.
Yes, Bob? Why didn't the Alpha work out the same way? Well, it did have a larger mass, but it also had a larger charge, and that larger charge created a larger force pulling the radius in and canceling out the other factors.
How do
It's
we,
like a satellite.
Yeah, it's exactly what it says. Amen.
so, I like totally forget chemistry.
Uh-huh.
So like the 4 is the mass, the 2 on the bottom is how many
Protons.
protons, and then that's electrons.
And that's the charge. No, it's actually protons minus electrons. So since the alpha particle has 2 protons and 0 electrons, it has a 2 plus charge.
But how would we have known alpha was that?
Because I told you.
But for last night's homework, we went,
Oh, it gave you actually. It said here 4 times the mass of the proton and a charge of 2e. So 4
That's
times the
not-
mass of the proton, charge of 2e.
how do you know it would be human?
Because you can look up on the periodic table as well as anybody else and say protons, 2 protons. Let's see, let's count like a chemist. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon.
I've only
And
got
that's
it.
how
Can you
chemists
do the
count.
whole periodic table?
What's that?
Can you do the whole periodic table?
No.
I can get
No.
it to neon.
I can do about half anymore. Is that a top chemistry
You used to teach chemistry too?
anymore?
You did? How long ago was that?
Before Miss Prentice,
How long ago
before
was that?
Mr. Story, before
Yeah,
Mr.
it's a
Searing,
time ago.
Before Mr. Dieter didn't.
before Mr.
I remember Mr. Dieter. I never had him.
He wants to announce it.
Did Mr. Dieter also teach geometry?
He's a geometry announcer too, correct?
Okay. Any other questions on 18?
Are we gonna have a?
My only other real problem was,
Yeah, I hear for well, I don't have for algebra one.
I guess are we just going over all these?
No.
Okay.
I want to
So I just have 2 other questions.
take your attention for 2 points. One is equation 20-7 in your book. On Friday, when I presented force between 2 current carrying wires, I assumed that the current between the 2 of them would be the same. What if it's different? Well, we're going to use the same reasoning, but we'll end up with a slightly different formula right here. If I have 2 wires here that are carrying current in the same direction, then as we argued on Friday, they're going to experience an attractive force between them. And we argued that from the right-hand rule. And if I compute the field created by one wire at the distance d here on the other, then that field is mu 0 I over 2 pi d, and that's Ersted's law. If I now come back and compute the force, that force is given by VIL, and if I plug in, then what I get is mu 0 I1 I2 times L over 2 pi d. Here's where the difference happens. Because my 2 i's were the same, I had I squared, which makes a lot of sense, but this is a more general result right here. That's the only difference. And now if we do exactly what we did on Friday, divide both sides by L to get the force per unit length, and cancel out the factors of 2 pi, then we get this expression right here, which is the equation 20-7. So I just wanted to alert you to the fact that when you look at 20-7, it's using 2 different currents of the wire, which is more general. That's perfectly fine. Now, I'm not going to say the same complimentary things about force law. Right-hand rule. Yeah. If you take a look at page 562 in your book, it gives you 3 right-hand rules.
So for you did it differently. You
Page
used both hands.
562 is spelled with a 6 and a 2.
But Mr. Campbell, I realized for you, whenever it's negative, you use your left hand, and whenever, because I like what you do it, because it doesn't change the. Am I on the other? Can we go over number 33? Or is that?
We'll see if we have time.
I do.
Now, the way I've done the field and the force is like this. If I have current through a wire, I can put my thumb in the direction of the current, wrap my fingers around it, and now I know which way the field is going. Deja asked about the direction specifically, so let's take a minute to make sure that we're all on board with this. In this particular case, I've got I going that way, so I wrap my fingers, right? And I look and I see that my knuckles to the right of the wire are going that way into the board. So I'm going to draw field going in on that side of the wire. And my fingertips on this side are coming out at me, so I'm going to draw a field coming out on the top of the wire right there. Does that make sense? Everybody clear on how to draw that? I want a yes or a no. Yes.
Nod.
Yeah. Current is going this way, here goes the thumb. Wrap the fingers around it. Do it. All right. Right hand. Right hand. Now, your fingers are pointing towards you, right? And they are above the wire?
Yeah, the wire's like.
Yeah, so the field is going to come out above the wire. It's going in below the wire. All right. Good? All right. Meanwhile, for force, now, this corresponds in your book, page 562, to number 1. They do exactly the same thing that we do. And that's cool. With regard to force, what I've told you to do is to take your fingers and put them in the direction of B, and take your thumb and put it in the direction of the velocity of the particle or the current, which is much the same thing, right? And now your palm is going to push in the direction of the force. If you take a look at numbers 2 and 3 in your book, they do funky things where the thumb goes in the direction of F, but it's a different one for current and moving charged particles, and just ignore all that. Ignore 2 and 3, and use what I've given you here.
Yours makes sense.
Yeah. Now, Peter Chen asked a really good question. Oh, so in terms of doing it, if I have a charged particle going this way and field going that way, I put my fingers in the direction of B. I turn my thumb so that it's in the direction of the velocity, and the force is pushing in. And I can mark that like so.
Even though that's like a really awkward hand.
It is an awkward angle for the hand. Now, Peter Chen asks, what happens if the B changes angles? So let's take our B and let's rotate it. What changes? The direction of the force does not change. Because if I place my fingers this way, notice I've got an angle between these two, but my palm is still pushing inwards. What does change, right, exactly, is the magnitude of that force, not the angle as long as it change. Well, if your magnet's rotating. Which is exactly what happens in big stands. Where will the minimum be? What angle will hit the minimum force? 0 degrees, when B is exactly parallel or anti-parallel to the velocity.
But no matter what angle you change it to, the force will always be.
The force pushes in. Well, until you hit 0, and then once you hit 0, if my B starts like this, then to get my thumb going right, I have to flip my hand, and now the force goes out. So the force will go in for all angles between here and here, and it will go out for all angles between here and here. Yes? Okay.
So, and for yours is a bit different because they say yours is both kind of like left hand and right hand rule, right?
Right, so left hand is appropriate if you have a negative charge.
Yeah, because that's
If you want to take your fingers and or your hands and write plus and minus on them, that's totally cool.
Wait, really? We can count in? I'm gonna do that to see if they'll yell at us. Yes,
You can do it, but you also have to write R and L on your shoes.
Or right, give me your
Right high across your fingers and B on your thumb. Or the other one. B on your fingers.
I guess I can't stop that, can
You can start.
Oh, you
something
could just call cheating.
And then F on my palm.
But he gave us permission.
I? And you gotta have on your shoes. Right. All right, I want to talk about Ampere's law now. And I'm just going to clear this and do a new one. We are going to do a little bit with Ampere's law to get you used to the concept. But we're going to do the full mathematical treatment of it tomorrow when we have more people. Lacrosse,
Baseball, softball.
softball.
The baseball team got off at 11:30.
Yeah, that's ridiculous.
Why?
And then lacrosse got out at 1. I don't think that's in there.
No, 1:30.
Yeah.
Okay.
Girls got out at 1:30.
I want you to imagine for just a moment that we have a wire carrying a current straight at you. Now, how would this actually happen? It would actually happen if you have like X-ray vision and you're looking at a circuit head-on and there comes the wire with the current coming at you. So
Taser.
it's physically not very, I guess,
What do you mean? Charges counting.
yeah, taser would qualify. Alright, good.
Yeah.
Now, first question for you. What does the field look like around this wire?
Appreciate.
Well, it
Well, if
was,
it's coming straight at us.
It's going to be curling around it. It's going to be curling around it counterclockwise. The last thought you ever had. The field is counterclockwise.
Watch that actually be my last thought.
Funny things I thought that like right before you said it too.
What's that?
I thought that right before you said it. It was like word for word. They shot through the
Now, we already know that the amount of field, the magnitude of field that you're going to get is equal to mu 0 I over 2 pi I. So that's what Ampere does is he generalizes it using a very cool calculus idea.
Oh no.
And what we're going to do is we're going to take and make an arbitrary path around this is arbitrary. It could have been drawn any old way, except for it has one requirement. It has to be a closed path that does not intersect itself.
Couldn't it just be a circle?
Yeah, it sure could, and we're going to do that in just a second. But I'm doing the general case right now. Arbitrary, closed, non-overlapping path. All right? Now, what I've done is to make my path out of straight line segments because that's all that we can handle without calculus. But if we could do calculus, we would prefer smooth curves because we like this. And then our quote line segments would be small infinitesimal.
Could you just do like square?
Yes. And square works. That's an arbitrary path. Right. That's an arbitrary path that is non-intersecting and it's closed. Right. I could also do a triangle, a dodecagon, not a dodecahedron. What's that?
Parallelogram.
A parallelogram. I can do any of those.
What is the?
Now, here's what I'm going to do. For each line segment, compute this product B parallel times delta L. Now let me explain that. This is line segment number 1. So this is delta L number 1. And at this point, B goes that way, because we know it's going around the circle, right? So if I take this, let's call that B1. If I take this out of the circle, and I move B1 so that it's tail to tail with delta L1. Now, delta L1 is a little bit more angled. Then there is a component of B that is parallel to delta L, and that component is like so. This is B perpendicular here, and this is B parallel right there. And what we're going to do is we're going to take just the B parallel part, multiply it by the delta L, and that is for one line segment. Now we're going to take all of those products and add them up. If I number my segments 1, 2, 3, dot, 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 all the way to n, here's my last line segment, right before number 1. And I sum up from I equals 1 to n, B parallel times delta L. Then that sum right there, here's Ampere's law, is magically equal to a constant mu0, we've seen that constant before, times the current enclosed by the arbitrary path. Okay? Is that okay?
You're never going to prevent that, believe me.
I'm hoping for it. Thanks. All right. Now, the question you may have is, why do we want to do this? Who cares? That's fine. And tomorrow, we're going to go into more detail as to how these calculations are going to work. Today, I want to convince you of a couple of things. Well, really of one thing. I want to convince you that Ampere's law is actually the basis for Ersted's law. I'm going to use Ampere's law to prove that this is true.
You're going to do that tomorrow, though.
I'm going to do it right now.
Right now.
Because it's nice and short. So here we go. We're going to take our wire carrying the current out at us. And now what I'm going to do is to make an arbitrary path around that wire that is the sensible one, a circle. Here's my arbitrary path. Now the reason I choose a circle is really simple. I reason from symmetry that the magnitude of the field has to be exactly the same at every point around the circle. Do you see why? If I turn my head, it's the same thing. So the field can't be different at different points. And I already know that the field is going to go around counterclockwise like so. So if my arbitrary path is a circle, let me take that circle and represent it as approximately a bunch of straight line segments like this. Delta L1, delta L2, etc. All the way around to delta Ln. Okay? And if I now compute B parallel times delta Li from 1 to n, according to Ampere's law, that has to equal mu0 times the enclosed current. And the enclosed current is exactly the current that's coming out of it. Now, so a couple of mathematical things happen. Thing one, because B is a constant value, I can pull it out of the sum. And the second thing that happens, it's mathematical, is because B curls around the circle, it is always exactly parallel to the delta L that is going around the circle. Which means the cosine of the angle between is always 1. And so it's invisible. And then finally, the last mathematical thing that happens is that what I'm left with is adding up these line segments that go around the circumference of the circle. Well, gee, when I add them up, I'm going to get the circumference of the circle, which is equal to what value?
Pi d.
Pi d, or in terms of the radius, 2 pi r. Right? Well, that's convenient, because I can now solve for the field, and when I solve for the field, would you look at that? The field is equal to mu0 I divided by, 2 pi r. Yep, that's exactly Ersted's law. Which means that Ampere's law is a more general version than Ersted's law. It gives us Ersted's law. It's also going to give us some more stuff. It's going to give us a field for a solenoid, which we'll talk about tomorrow. All right? Have a good day.